Welcome to PGHDOTNET user group. Today we're going to have learning functional programming through construction first principles with our seasoned speaker, Cameron. Hey, welcome, Cameron.
Yo, good afternoon, good evening, everyone. How's it going?
Pretty good. Thanks for joining us today and going through your functional programming.
Yeah, I'm definitely looking forward to it. This is one of my favorite sessions to give, especially if you've heard about functional but don't really know what it's all about. This is a great session.
Awesome. Off to you.
All right. Well, with that, we'll go and get started. So my name is Cameron Presley, and if you're in the right rail yard, you're here to learn about functional programming through first principles. So a little bit about myself. I am based out of Charlotte, North Carolina. I've been in the tech industry in some shape, form, or fashion for like over 15 years now. Feels a little bit odd saying that. I'm the owner of a company called Small Batch Solutions. So what is it that we do? We actually help companies get their projects back on track. So if you've ever worked on a project or an initiative and you're thinking, oh goodness, this is starting to go a little pear-shaped, it'd be really great to bounce ideas off someone who's a little bit more seasoned, has a little bit more experience. Come chat with us. That's what we do. I am also a Microsoft MVP. What does that mean? That means I've spent a lot of time giving back to the community, either through open source development, speaking at user groups and conferences like I'm doing this evening, and overall just trying to level up the community. Because when I got started, the community helped level me up, and this is my way of giving back. Last, but not least, I'm also an amateur woodworker. This is like one of my first projects, and you may be thinking, Cameron, why are you showing us this workbench? And I show you this because as you learn something new, you're going to struggle at it. It's not going to look the best, right? This workbench has like a wonky wheel. There's miscuts. There's weird gaps. But the skills I learned here help me make much better projects in the future. And that's a really good way to think about today's session. So enough about me. Let's get into it. First things first, no need to take notes. For those playing along at home, you are more than welcome to scan this QR code, and it'll take you to everything you're going to see here today. Slide deck, source code, recommended books, articles, things like that. If you're a little bit more security focused and don't necessarily want to scan a random QR code, you are more than welcome to go to this link below, blog.softwarementor.com/presentations. And it'll take you to the same resources. So let's set up our scenario, right? We are volunteering at a robotics club, and we're going to help build a rover. Now, the way I like to learn new stuff is I like to go through like scenarios, right? Real things, not just tutorials. So in this instance, we're going to have to develop some type of API that knows how to take commands we're going to send from Earth to instructions that can be understood by the rover. Now, the good news is we've got a bunch of hardware engineers that are going to make the rover. And that's great because I'm like partially colorblind. You don't want me wiring up anything. So we're going to focus mostly on the software here. So in order to do that, though, we've got to really think about what are some constraints. And one of the constraints we're going to put onto this problem is this idea of correct by construction. I want us to design our code in such a way that engineers can't ship bugs to production because if they actually wrote a bug, the code won't compile. Now, in some languages and some approaches, this isn't always feasible, but I found that if we put this constraint in play, we actually end up with more robust code that is less likely to break, less likely to fail. And I don't know about you, but if we're going to try to break something, I'd much rather figure out that we broke it before we ship to production, right? And I'm not the only one who's got ideas like this, right? Jeff Atwood in the Coding Horror blog that he's been doing for good grief, at least 20 years now, at least, has a really great blog post called Falling into the Pit of Success. And there's a great excerpt where he mentions that a well-designed system makes it easy to do the right things and annoying, but not impossible to do the wrong things. In other words, if we design our system in such a way that's easy to do the right thing, guess what? Other engineers are going to do the right thing. And if they need to do something that's bad, we're going to make it really annoying, or it's going to be very awkward to do it. That way, we're always putting them on that success track. So let's take a look at the requirements for our rover. Now, we know the rover is going to have some initial starting point, an X and a Y. So this is like a two-dimensional plane, right? We're not going to worry about height or a Z-axis or any of that such. And we know the rover is going to face some type of direction, north, south, east, and west. So we're not going to worry about like certain degrees or radians or any of that such. And there are 4 key commands that the rover is going to have to be able to understand. The rover is going to be able to know how to move forward and backward, right? And in those cases, it'll change its Y values or X values, depending. And then the rover is going to be able to turn left and right. So when we're turning, that's not going to impact our location or starting point, but it will impact what direction we're facing. And we'll take a deeper look at all of these requirements a little bit deeper in the presentation. But the big thing to note here, right, is that we just got a rover. It's got an X and Y. It's got to have some directions facing. Looks like we have some commands, and those commands will have certain business rules. Now, when I approach problems like this, I like to do some domain modeling. And no, it doesn't necessarily have to be domain-driven design, though if you want to go down that route, you can, though this domain's too simple for that. But what I like to do is I like to think about the nouns, right? What are the specific verbiage, right? Terminology that is specific to this problem. And in our case, there's 3. You could argue that maybe there's a 4th one for like location or position. I didn't come up with that, but you may have came up with that. And there's some relationships, right? So we have this concept of a command. We have some concept of a direction. And we have this idea of a rover. And that rover has a direction, right? It has that property. That's why it has an arrow pointing to it. What I've found is once you have these nouns and you have a little bit of the relationships, the way to implement it is that you actually flip it, right? So everything that doesn't have dependencies are on the top, like we see on the right, and everything that does have dependencies are on the bottom, like we see at rover here, right? So in order to build rover, we got to have direction first. So let's start implementing these things. Now, when we take a look at direction, right, direction can only be one of 4 set of values, right? North, south, east, west. It can't be anything else. So right off the bat, if I were trying to model this, there's a couple of types that I would not want to use, right? I wouldn't want to use string, right? I don't want to model my direction as a string. And the big reason is because if I model as a string, we then start thinking about what could strings be, right? They could be anything. And that's not great because we know direction can only be a set of specific things, right? So in that case, I'm probably going to use an enum, right, from C#. So we can say public enum direction, north, south, east, west. And this is actually a pretty good start because just by doing this, we've already eliminated a slew of issues. For example, let's say I have some C# code and I try to declare a variable called start, type of direction, and I give it the string of kumquats. I'm already getting some hiccups from the compiler saying, hey, wait a minute, you can't do that, right? A string is not the same thing as a direction. And that's a pretty cool thing. We've already reduced and removed some cause of errors in the system, right? We can do a similar thing with command, right? So command can be one of 5 possible values, right? You got move forward, move backward, turn left, turn right, and then quit, right? Because at some point the rover's going to quit doing things with commands. Since it can only be one of a specific set of values, we can also leverage an enum here. And that's what we're going to do, right? Public enum command, move forward, move backward, so on and so forth. And very similar to direction, if I try to create a command, in this case called platypus, we're going to get the same error, right? Like, hey, you can't convert a string to a command. It doesn't work that way. Now, I mention all this because enums are pretty cool, but they do have some limitations because under the hood, enums are just numbers. In other languages, TypeScript is a great example of this, but other functional languages, they will have a concept called a type union or a sum type. Now, this doesn't quite exist today in C#. However, there is a proposal for this on GitHub that I believe has already been approved called type unions for C#. If you've not taken a look at this proposal, I would highly, highly encourage it. With this and the advanced pattern matching that C#'s gotten in, I believe C# 9 and 10, working with union types is going to end up solving a lot of problems that we run into today. So I'm just throwing it out there that even if this concept doesn't make a ton of sense right now, this is coming down the pipeline, which I think is pretty cool. So at this point, we've got direction, we've got command modeled, but now we've got rover. We've got to model rover somehow. And rover's interesting because it's not just one of a possible set of values, right? Direction could only be one of 4 things, command could be one of 5 things, but rover's got to model like permutations, right? Because it's got to model all possible x's, which are numbers, all possible y's, which are numbers, and all possible directions, right? And it's this combination of types that when we start thinking about this, like x and y in direction, we're going to use a record. Now, in most functional languages, this may be called a product type, but you're going to use some type of model here where it lets you take types and combine them into new types. So even if you've never worked with records before, here's one way of defining it, right? It's got a public int x, int y, direction. In fact, this looks a lot like a class. The only difference, though, with records, at least the way we've defined it so far, is that it'll actually do value comparison and not comparison by reference. So that is one of the values there, or one of the benefits. And there's some cool things, right? So if I try to create a new rover, and let's say I try to set a property on it called number of wheels, can't do that, right? Because in our initial definition of the rover type, there was no property called number of wheels. So once again, we're limiting what developers can do. Now, if they want to set number of wheels, they got to go back to the rover type definition, update it, so on and so forth. And they can if they need to. But let's take a look about some code that shows a deficiency with how we've set up rover. So let's say I've got this void method called log, takes in rover. It does a nice console write line. It says the rover's at some x and y facing some direction. And we increment this x by 1. Now, if you've written C# code before and you're looking at this method, this looks a little bit odd, right? Because we said that this is a void method called log, but it's permanently changing my rover, right? Every time I call log, it's actually going to change my rover's x value. And so if we think about that from like a real world scenario, let's say I had some logging going on in my application, maybe because I'm troubleshooting. Every time I'm logging the status of my rover, in real world, my rover would start moving on its x-axis one step at a time, which seems a bit odd, right? Like that doesn't seem correct. So what could we do instead to fix this problem? Well, let's change our rover definition a little bit. So if you recall, our properties were get set. Instead of get set, we're going to make them get init. And the minute we put this init modifier, we're essentially telling the rover type that once you set an X or a Y or the direction, that's it. It can't change again. You can kind of think of this from a read-only property from your object-oriented backgrounds, right? And the minute we make this change and we go back to our log method, we see this fun little error now. And it says like, hey, you've got this init-only property X, but it can only be assigned when you're initializing the object, but you're trying to like change it here. You can't do that. And this is pretty cool because this is where the compiler is really shining, right? It's saying like, hey, this is only supposed to be set one time. You're trying to set it here. You can't do that, which then forces the developer to make a choice. We either get rid of this line of code, in which case log now does what's supposed to, log, or let's say that we really wanted to change that X value. Well, here's how we would do that. We would update our log definition to say that it returns a rover now. So now this is a function that says if you put in a rover, I'm going to give you back a new one. And to change that X value, we're going to use this with keyword. And this only works with record types. But essentially what we're telling C# to do is say, hey, we want you to create a new rover instance with all the previous values of the existing one, but we want you to change only the X and let it be this +1. Some people will sometimes ask, like, isn't that intensive on memory or other resources? In some languages, it can be. In C#, not so much, because they use a technique called smart pointers. If you want to know more about that concept, hit me up in the chat and we can kind of geek out about that a little bit, because it's a really cool idea. But suffice to say, using with records, that's not going to be a performance hit. So why is this important? Right. Joel Spolsky, you would know him from two things. If you've ever used like VB in Excel, he kind of helped write that. He also was responsible for some of the work on Stack Overflow, right? So he's kind of a pretty well-known figure in our industry. But he argues that you deliberately architect your code in such a way that your nose for uncleanliness makes your code more likely to be correct. And this is the real art, making robust code by literally inventing conventions that make errors stand out on the screen. Essentially, make wrong code look wrong. And if we go back a little bit, even if you're not a C# expert, this code looks wrong, right? This would absolutely get flagged in a pull request, which I would argue that means we're doing our job based on how we've defined our types and such, which I think is pretty cool. So you may not have realized it, but you've actually learned your first functional concept, this idea of immutability, right? We say that an object is immutable when after we've created it, we can't change its state. And you may be thinking, well, that doesn't sound super useful. But actually, when you start working with immutable types, a whole slew of problems actually just disappear. They go away for you. And the biggest reason why is because keeping track of changing state is hard. If you've ever worked in a code base that had global state, anybody ever worked with a code base that had singletons running around and those singletons were being accessed in other places of the code, and this part of the code could change it here and this other part of the code would change it over here, and you had to keep track of all that? Yeah, it can get really complicated. So by making your code immutable, you kind of ditch this whole keeping track of changing state. So that's an advantage. And by ditching this, it actually makes your code a little bit easier to understand what it's trying to do, which is kind of nice. At this junction, when I look at our requirements, we've already knocked out this first requirement, right? We defined our types, and we can create a rover at a certain X and a certain Y in a certain direction. Trivial, we can do that. So let's take a look at this next set of requirements, right? We've got to implement some way for the rover to move forward and backward. And we're going to really focus on this move forward bit. Now, for this requirement, when we move forward, it's really based on the direction we're facing. So for example, if we're facing north and we're told to move forward, our Y value needs to go up by 1. If we're facing south, told to move forward, our Y value is going to go down by 1, right? So we're just pretty much going up and down. East and west is exactly what you think. It's just going right or left, and X value is increasing or decreasing appropriately. Just think like a number grid. Now, we could go start writing code for this, but before I do, I like to start thinking about this in a little bit differently, right? I like to think of this idea of a mapping. And I usually come into this when I know that I've got to come up with a new value based on an old value. Right. So since we know the rover is going to move and the rover is immutable, that means we have to return a new rover. Right. So we're going to have some mapping that says give a rover, return a rover, which is really cool because that's what our mapping is going to look like. So I've drawn a circle here that's going to represent all possible rovers. And here's a second circle that represents all possible rovers. In that first circle, I'm going to break all possible rovers down. I don't care about their X or Y value, but I'm going to break them down based on their direction that they're facing. And then on the right, I'm going to break all the rovers down based on whether a Y value or an X value is changing. And then when I start thinking about my mapping, right, I'm going to start drawing arrows. So if my rover's facing north, I know it needs to map to rovers where their Y value went up by 1. And if the rover's facing south, Y value -1, so on and so forth. Now, once I've done this mapping, the question I get to ask myself is the following. Is everything on the left mapped to a single thing on the right? And if the answer to that question is yes, then some really cool things become available because we actually have a function. Now, when I say the word function, you may be thinking like the keyword, right? Especially if you're in other languages besides C# and .NET, right? Like, or frameworks. But when I talk about functions here, we're actually talking from a mathematical sense. So if we go back to our mathematical definitions of a function, we get something like this, where a function is a mapping between two sets such that every element in the first set maps to a single element in the second set. And you might be thinking, but Cameron, we're not dealing with sets, we're not dealing with elements, we're coding, right? I'm not a mathematician. Well, let's change this definition a little bit to make it a little bit more clear. So instead of talking about sets, let's talk about types, right? We're saying that a function's a mapping between two types such that every value of the first type maps to a single value of the second type. If you've got this, you've got a function and a lot of cool things open up. But let's take a look at mappings that aren't functions. Let's say that we were trying to map how many days are in a month. So I've got one circle that's going to represent all my months, and I've got another circle that represents the number of days. So here's all my possible months. Don't worry about the fact they're in a different order. The order will make sense in a minute. And here's all the possible number of days, right? Because no matter what month, there are no months with 27 days. There are no months with 32 days, right? We can say that every month will have either 28, 29, 30, or 31 days in it. And with that, we can start doing our arrow mapping, right? January has 31 days in it, right? That's fine, no problem. March also has 31 days. So far, so good. We have a function because everything on the left so far is mapped to a single thing on the right. It's okay if they map to the same thing. It's just as long as it's mapped. April gets mapped to 30. So far, so good. And everything's fine until we get to February. And this is the problem, right? Because February maps to 29 or 28 days. So how many days does that month have, right? You don't really want to work with code that sometimes gives you an answer and sometimes it doesn't, right? Because this makes troubleshooting harder. And the problem with this is the fact that the month of February is not enough information, right? If you just tell me February, I can't really know if it's 28 or 29 days. I need to know the year. And specifically, I need to know whether it's a leap year or not. And if I know that piece of information, I can tell you the answer. But without it, it depends. So, and I want to take a moment to talk about another thing here. Let's say I try to write this code, right? Let's say I try to write this function in C#, and I do a switch statement on the month names, and I go through, and I get to February. How would I know? I would either always return 28, which means I'm wrong about a quarter of the time, or I'm going to do something like datetime.now to get the year. Well, the minute I do that, any of my unit tests get weird because now I'd have to figure out some way to mock out datetime.now or realize that my test is going to fail when the new year clicks over, depending on whether it's a leap year or not, right? All that sounds pretty frustrating to me. So let's take a look at another example of a mapping that didn't quite work out. Let's say that we were wanting to map numbers to month names. So I've got one circle here to represent all possible numbers. I've got another circle here to represent all possible months. So on the left, I've got numbers 1 through 13. Here's some possible months. And I can start drawing arrows, and things are pretty good until I get to 13, right? What does 13 map to? Well, argument exception. Because I don't know about you, but I don't know any month that has the number 13 in it. Now, in most datetime libraries, they do like round robin. So once you get to 13, it essentially treats it as 1, but the year increments. But technically, there is no month with number 13. But the problem here is that we said we can support all numbers. That's not true. We can only support some of the numbers. So what happens when we get a number that we don't know how to support? Do we return null? Well, null's not a month. Do we throw an exception? Well, last time I checked, there is no month called argument exception. Right. And this is where things start breaking down in our code, is because we say that our code can do one thing, but it really can't, not always. And C# in particular, other languages have this next problem though, is it's not always clear that the code we're calling is going to throw an exception, right? Unless you're reading the docs or looking at the IntelliSense in your code editor, you're calling a function that may throw. In Java, they have this idea of checked exceptions, which means if you call a function or a method that can throw an exception, you as the caller have to handle that or the code won't compile. Now, there's some really bad anti-patterns that developers will do to get around that, but at least it's something. In C#, it's kind of Wild West, right? It'll just work, or not in this case. So we will see a little bit later on in this presentation how to solve this. But for right now, we're going to go back to move forward. All right, so here's our move forward mapping, and we can actually write the code for this because it's a pretty straightforward function. So here is just a static method called move forward, takes in a rover. We're doing a switch on direction. And there's our 4 cases, north, south, east, west. And then we return a new rover with the y or x value changed as appropriately. If you're in a newer language, a newer version of C#, you can also use this nice condensed alternative syntax for switch statements. Looks more advanced pattern matching. One thing you might notice in both cases, though, is that there's a default, right? And in the case on the right, there's an underscore. The reason why we have to have this is because enums are not exhaustive in C#, right? Because you can always take an integer and typecast it as an enum, and the compiler will happily go along with it. That's why we need the type unions that I showed earlier, is because when we have type unions, you would never run into this problem because type unions and pattern matching are exhaustive at that point. So I just wanted to call that out here. And why does this matter, right? Why am I spending so much time talking about functions? It's because I hate debugging inconsistent behavior, right? I don't like getting bug reports because that means as a developer, I messed up, right? It's even more frustrating when the bug report isn't consistent, right? It's like, well, sometimes it breaks this way, but sometimes it breaks a different way. It's hard to troubleshoot. It's hard to reason about. It's even hard to explain to users why it happened, right? I don't like dealing with that. So if I can design my code to prevent that, I'm going to do that. And functions are a pretty good way of handling that. The other reason why I think this is important is because we're using a typed language, right? C# is statically typed. So if we're going to take on the tax, if you will, of working with the compiled type system, it'd be cool if the type system actually helped us here instead of just saying, like, maybe no, hopefully figure it out. No. I want to put that in my type system. So we've implemented move forward. Move backward is going to look very similar, so I'm going to skip that. And now we're going to take a look at turning left and turning right. So the requirements for turning left are the following. If the rover is facing north and you're told to turn left, then we're going to face west. And then if you're facing west, you'll go to south, south goes to east, east goes to north, and you're going to go in a circle, right? So these are our requirements. So let's do that mapping exercise again, right? Here's all my possible rovers on the left, possible rovers on the right. All the rovers on the left are broken down based on what direction they're facing. All the rovers are on the right are also broken down by the direction they're facing. I'm going to start drawing my arrows. Same question as before, right? Is everything on the left mapped to something on the right? Yep. And it's only mapped to a single thing. Because that's true, we've got a function. So writing the code for this is pretty straightforward. In fact, it looks a lot like this. The other thing I want to call out here, especially since we've gotten turn left done now, is for those of you with an automated testing background, right, unit testing, how hard would it be to test this? Right, this is a static function. You have full control over the rover, which means you have full control over the direction, right? So it's a little bit more complicated than, let's say, FizzBuzz, but not by much. It couldn't be. And what you'll find is that when you have functions kind of set up like this, you'll find testing becomes a lot easier. In fact, sometimes it's trivially so, which is pretty cool. So at this point, we've got turn left, turn right's going to look very similar. And we've got a bunch of pieces, right? We've got a bunch of functions running around because we got to move forward, we got to move backward, we got to turn left, turn right. But we don't have a program yet, right? We don't actually have an application I can give to the user to start playing with. So in this next part, we're going to talk about how do we glue all this stuff together into a pipeline. And at a high level, here's what's going to end up happening, right? We're going to get the input from the user. And then based on that input, we got to figure out which command do they give us, right? Was it the move forward command, the move backward command, so on and so forth. And then once we have that command, we got to map it to one of those actions that we wrote, right? Is it the move forward function, the move backward function, which one? And then once we have that function, we're going to invoke it with that rover, right? With whatever state the rover's in now. And then when we do that, we're going to throw out the old reference and have the new reference. So let's start going through that a little bit. User entering input, console read line, right? Nothing fancy, nothing complicated, right? It's just some function, some code that when invoked gives us back a string. Could be coming from a file, could be coming from a database. We do not care. We're just getting a string from somewhere. Input is mapped to a command. Let's take a look at this one. So this is another one of those mapping things, right? And if it's coming from the user, it can be any string. So that's what the circle on the left is. It's all strings. And then we've got a circle on the right for all of our possible commands. So I'm going to start drawing my arrows, right? So possible strings are F, B, L, R, and Q. Possible commands are move forward, move backward, turn left, turn right, and quit. And I can start drawing my arrows over, and things are fine. But remember, the circle on the left is for all strings, which means I can have a string called do a flip. Well, what command does that do? Right? We never told the rover on how to do a flip. And this is just me being a little bit cheeky, but remember, these commands are coming from the users. We can't trust them for anything, right? Those strings could be anything and everything under the sun, but we don't have a way of handling that, right? So what do? You're going to run into this problem all the time with this approach, right? Is that sometimes you're getting data from a source that you can't always trust, and you got to coerce it or convert it into something that you can. So you got to figure out a way of handling that scenario. When this happens, you've got two choices. One approach is you actually restrict your input so that it can only be valid things that you can work on. You kind of saw an example of this earlier when we were modeling direction, right? Instead of making direction a string, we only said it could be like an enum of 4 values. And that's all well and good. But in our case, the problem is that the users are unpredictable, so we can't restrict the input. And if we can't restrict the input, that means we've got to expand the possible returns, right? The possible outputs. And there's a ton of ways of doing this, right? You actually do this all the time in your C# code. If you've ever had a function that returned back a string question mark, right? Like it could be a string or null, right? You've done this approach. But I don't really want to do null. So I'm going to think about what's the easiest thing we can do here. So I'm actually going to update our command enum to have a new option called unknown. Because when I think about it, if I get a string, I don't know what it is, then it's an unknown command. You've told me to do something I don't know how to process. And this also kind of works because from like a business rule perspective, this kind of jives, right? I can talk to a business analyst or a product owner and be like, hey, if we get something that we don't know from the user, that's an unknown thing, right? And 9 times I'll tend to be like, yeah, that makes sense. So once we've added unknown, we go back to our mapping, add unknown to the commands on the right, and now we can do a flip to it. Okay. And in fact, we can map all other strings that are not F, B, L, R, and Q to unknown. Now that we have this, everything on the left is mapped to a single thing on the right. Bingo, that means we have a function, so we can actually implement it. And here's what it looks like. So we've got a function called convert string to command. You give it a string, and it's going to check the string. If the string is null, it'll substitute in an empty string. Otherwise, it'll trim it to lower it, and then we do a switch. And if it's F, B, L, R, Q, we return the right command. And then otherwise, our default is going to be that command unknown. That's a function, right? It handles all inputs. It's not going to throw exceptions. It's always going to return you back a command. That's awesome. So we've got getting a string from a user. We've got mapping that string to a command. Now we got to map that command to one of those functions we wrote earlier, right? So here's our circle for all commands. And then here's a circle that represents all of the functions that we've written that says give a rover, return a rover. So here's all the commands on the left. Here's all the functions we wrote on the right. And as you can imagine, we start writing these arrows pretty cleanly, right? The move forward command means we get the move forward function. The move backward command tells us we get the move backward function, so on and so forth. But we've got a problem. What does quit and unknown map to, right? If we get the quit command or the unknown command, we definitely don't want to do any of those 4 things. But we can't just have the rover crash either, right? Because rovers are expensive. We don't want that to happen. So we've got to handle this. We can't restrict the inputs, right? Because even though we're controlling this in our system, quit and unknown are valid commands. That can absolutely happen in our app. So we can't restrict the input. That means we got to expand the output again. So we're going to think about like what function should we return if our commands quit or unknown. And when I think about it like pragmatically, if I'm told to quit, or if you give me a command that I don't know how to process, I'm going to do nothing, right? I don't want the rover to move. So let's write that. And here's that function. It's called do nothing. It takes in a rover and returns a rover. This function may look really dumb, but this concept comes up so much in functional programming. A function that takes in an item and returns it back, so common, it actually has a name. It's called the identity function. But let's see what this may look like in our code, right? So once we have the do nothing function, we can update or convert command to action function, do the following. Switch on command. If it's move forward, backward, left, right, or quit, or sorry, forward, backward, left, right, calls the functions we've already written and tested. Quit and unknown goes to do nothing. And because enums are not exhaustive, unfortunately, we also, our default is also do nothing. Pretty straightforward, not too terribly bad. Now we've got these last two steps. Hey, we've gotten this function, we got to invoke it with the rover, and then we need to update the rover with a new state. So I can kind of talk to you about it, but I'd rather just show you the code at this point. So here's our application, right? We've got the rover, and we've created it at 0, 0 facing north. Our initial command's unknown. And while the command's not quit, we're going to print the rover, display the menu. So you can think of those things as like your UI, right? We're going to get the input from console. And then we're going to, there we go. Input from console. We get our command by saying, cool, hey, converters, convert that string to a command. And then we say, hey, now that we've got this command, hey, action, what action should the rover take? And then the last part is where we throw out the old reference and use the new one. And then we've just got this loop, just always running until the command gets quit. And that's it. It's actually not too terribly bad. And the nice thing about this is that if we have a bug, it's pretty fast to figure out where we may have broken something at, right? Because if we're calling the wrong function, it's because there's an issue in our mapping logic, right? And if we get like a command that doesn't map to anything, it's because our convert string to command is not working. So you can actually like pretty quickly narrow down issues there, which is nice. So this is our solution if we're getting input from the user, but let's tweak this a little bit. Let's say that we knew all the input ahead of time. Let's see what that solution would look like. So it would look something like this, right? We've got our input string, our input string of some Fs, Ls, Bs, whatever. And we've got our start, right? Still 0, 0 facing north. But now we can actually use some link to do some fun. So we're going to first take that big string of letters and we're going to convert that string into an array of its individual characters, right? So at this point, we have a list of strings. We then convert each of those strings into its specific command. We then take each command, convert it to its action, right? Whether it's the move forward, move backward, so on and so forth function. And then, sorry about that. And then our last one, that aggregate, is it essentially takes that rover and calls it for each one of those functions, and the return of that function is the input for the next one. So the aggregate's really our for each loop that we had before. And that works out like a top. But when we take a look at this code, here's something that looks a little bit odd. We've got like 3 select statements, right? We're going from character to string, and then a string to command, and a command to action. We can actually clean this up a little bit. Now, very quickly, there's no performance hit by having 3 select statements, right? Because given the nature of link and how it's lazy, it's not going to iterate the list 3 times here. It's actually going to iterate this entire list once, which is kind of nice. In other languages like JavaScript and TypeScript, for example, they are not lazy when you do this type of stuff, so it would iterate 3 times. But so a little brief aside there. But let's see how we can clean this up a little bit. So here's really what's happening, right? We've got all of our strings, all the commands, all the rover to rover things. So we're able to go from F to move forward, B's to everything else, L, so on and so forth. So here's what's happening. It'd be really cool if instead of having to do these like individual steps, we could just create one function that can go straight from strings to these functions. And we can do that using something known as compose. So here is an extension method that we can write called compose. And there's a lot of generics in here, but here's a really good way to think about it. If you give me a function that can go from A to B and another function that can go from B to C, I guarantee I can give you a function that can go from A to C. And you can kind of look at that return, right? Where we're going to say, here's a function that takes in some A, and it's going to call the G function with whatever the output is of the F function. That's it. Let's see how this code would actually be in use. So here is that solution again, except we've made some functions a little bit more clear, right? I've written 3 functions here. We've got one called toString that says if you give me a character, I will turn back a string. I've got another function called string to command that essentially is just pointing to the convert string to command function that we wrote earlier. And then I've got another function that really just points to our convert command to action. But the minute we've got these 3 things kind of called out, we can build a new function called multi-mapper in this case. And what it does is it does toString composed with string to command, composed with command to action. And once we have that multi-mapper, we can actually use it here. So instead of having those 3 select statements, we only have 1 now. That's a pretty cool improvement. And the reason why this works, by the way, is that all these concepts build upon each other. We can only compose functions if they truly are functions, right? Everything on the left has to be mapped to a single thing on the right, because if any part of that broke, then our composed pipeline would break, right? It wouldn't work correctly. So that's why knowing that we had functions allows us to do some cooler stuff like compose here. And with that, let's take a moment to kind of reflect back everything that we learned this evening, right? We learned a little bit about immutability. And really what that does is it allows us to remove the ability for outside forces to just manipulate state. And because we're removing that capability, that means the complexity we got to deal with is a lot less. We learned about functions, right? And they're really saying that we map everything from one type to something in the second type, right? Everything on the left is mapped to a single thing on the right. And then we learned about composition, this idea that we can take functions and compose them into bigger functions, or this idea that we can take small programs and compose them into larger programs. And with that, I want to say thank you all so much for joining me this evening. On this screen, the QR code on the left is once again straight to the slide deck and the resources. The QR code on the right, let's say that you saw something tonight that really piqued your interest, or you wanted to talk a little bit more about something. If you scan the QR code on the right, it will pre-populate an email that you can then put in some additional information, and we can continue having those conversations. But otherwise, thank you all so much for your time this evening. I really appreciate it.
Hey, thank you very much. It's been a nice session, man.
No, thank you.
Appreciate you taking this time this evening.
Yeah, absolutely.
We do have a couple of questions, Cameron, if you want to take it. There is one. I think everybody's interested about the smart pointers in C#.
Yeah. Okay, so let me back it up here real quick. So Kurt, your comment, discriminating unions exist in F#? Absolutely, it does. That's why I'm really excited about type unions, because they're going to bring that into C# correctly, because you can kind of muddle with it in C# today with it in F#, but it's not cool. It's just not as easy, I should say. Smart pointers. Okay. So this is a really cool concept. Let's say we have a rover, right? X, Y, and direction. Let's pretend each of those properties take a square block of memory, right? And now, so X has 10, Y has 20, direction has north. No problem. Let's say I want a new rover where Y is still 20, direction still north, but I want X to be 0. When it creates that second record, it doesn't create 3 new blocks of memory. It creates 1 new block of memory for the X of being 0, and then it reuses the same pointers for Y and for direction. So it's not 6 blocks of memory for the 2 records, it's 4 blocks of memory. And you can only get away with that because records are immutable. That's the only way you can get around that. Other languages also have this concept. Haskell is one that comes to mind. So yeah. So hopefully that helps out Jose on the smart pointers in C#. So that's like a compiler hack under the hood. So as a developer, it's not something you typically need to think about. Yeah, let's take a look at the chat. Yeah, too low for string comparisons. I guess this is functional. Yeah, I mean, you can, right? Like if you want to use like the string dot like compare ordinal, that is a pure function. You could still use it that way. I just did too lower because that was just what I had written. Let's see here. The next comment, you will allocate 3 enumerators that will have performance implication. Not really, or I would be surprised if that was the case, because at the end of the day, you're also calling aggregate, which is going to force all that to happen at once anyway. So I'm not quite sold on the fact that we would have 3 different enumerators. But even in the case we did, that's why the compose actually does help us out, right? Because that would actually reduce the number of selects down into 1. Yeah, was the bind in functional programming the same as aggregate used in LINQ? So not quite. Aggregate in LINQ is called reduce in any other language, especially like JavaScript, TypeScript, like that side. Bind, you can kind of think of that as flat map. So you know how in LINQ we have select versus select many? And select many is how you take like an array of arrays and turn it down to a single array. That's closer to what bind does. Bind is also it's a design pattern, right? So in object-oriented, we have design patterns all over the place, right? Factory patterns, singleton patterns, we've got like mediators, things like that. Well, we have design patterns too in functional as well. And the most common one is called a monad. And it's this idea of like, how do I attach some context to values? And then at some point, you want to take these 2 contexts and make them play with each other, right? Let them build, like interact with each other. And bind is a way of doing that. I do have a different talk that I like to give where we go a little bit deeper on how to make that work. So I don't know if that's something that might be interesting in the group at a later time, but that would be kind of like my...
Absolutely, we'll be happy to host that, man. Thank you.
Yeah.
Okay, I think that's the last question. Thanks everyone for joining us today, and Cameron, thanks for taking time and walking through the session, man.
Yeah, I really appreciate the opportunity, and I hope you all have a good evening. Until next time.
Yep, thanks everyone.